Alright guys, this is part 4 of the video here, assembly. This is actually, you have to pardon me here, this is during business hours at least to start the video here. So there might be some commotion in the background and some walking through and stuff like that. And the phone might ring, there might be some funky editing here through at least the first part of this video. But kind of under a time crunch here, so had to make do during the day here. So what I'm going to do is go ahead and we'll show you some of the preliminary things here while prepping the block to be assembled. There's gallery plugs and bearing installations and stuff like that we need to do here. So we'll go over that. Anyway, so yeah, stay tuned. Okay, so obviously being an engine block, it has internal oiling passages. If you look right here, this line that comes through the block, that is your main oil gallery, and basically that supplies your mains directly from the oil cooler, and then before that the oil pump, and obviously all that stuff. So, but there's little plugs in here. There's a plug right here at the bell housing. A lot of times people's turbo kits will tap in off that. And every main, if you can kind of look here, every main, there is a plug. So this one here you really can't tell because it's back behind here, but and this one actually doesn't have a plug. That's the one that's fed through the oil cooler. So and then basically what happens from there is, if you can look back here and see, you can see this line right here, and each one of your mains has one of those, and that's what feeds your cam bearings for your camshaft. So you have that, and then also we go to the front of the block, and you can see here, this is actually fed. See this casting here, and that's drilled, and these are your lifter galleries. That's what feeds your lifter's oil, and then your rocker arms from your lifters and so on. These also feed the oil cooler piston squirters. Piston squirters, not the oil cooler. So basically this comes out of this plug right there that feeds the mains. So you kind of see how the oil goes throughout the engine there. And what we have to do is go through and plug all these, because if you didn't, you'd have no oil pressure and oil leaks all over the place. So I'm going to go ahead and show you how to do that, and then we'll go so on and so on through this. One thing you want to do is to make sure that all these are blown out with compressed air, that you have no grit whatsoever in these things. And it doesn't matter how well you clean the block, you need to make sure of that, because there will always be little specks of stuff in here, especially if you've been moving the engine around and all that sort of stuff. So make sure you blow it out with compressed air. So we'll go ahead and get started. And I don't know how much narrating I'll do during it, but you can just visually see what I got going on, and we'll go step by step from there. Using Loctite 5452 thread sealant on these. It's some spendy stuff, but I like using it for all my pipe thread fittings versus Teflon tape or anything like that. It's just good stuff. that takes care of our oil galleries. Now on each side of the block, and don't confuse these for your engine mount holes, but there's a block drain on each side. That's to get all your coolant out of the block when you need to dry it up. I use a different, it's not an Allen head for these, I use just a typical hex. A little easier to get on with a wrench if you have to get in on it with it in the truck and all that. So okay, so now we're going to install the cam bearings. Cam bearings require this special tool to install, and they don't require it. You can, there's some methods out there where you can use like all thread and washers and kind of pull them into place. If that's, how you want to do it, then fine. These tools aren't too expensive, especially do a lot of stuff like we do around here. It's a really handy tool to have. So basically, one thing with the cam bearings is we have to make sure that the hole in the cam bearing, lines up this way and this way with the hole in the main bearing. Otherwise, it'll shut off all your flow to your cam bearings, and you will seize the cam up or spin the bearing or worse. So when you drive them in, we'll have to line them up, and we line them up by sight with a flashlight down in your oil supply hole, so we'll be able to tell that. So this special tool has a centering tool that centers off the front bore. The last one is kind of tricky. Usually you do it from the other side, but if you're on an engine stand like this, it's a little tougher. I've gotten pretty good at seating them straight just from the end, but normally you would flip this around and index off this last cam bore. That way everything's straight. So go ahead and do this. One thing to notice is the IDI has this fatter cam bearing. That actually goes to the front. Basically it's for the extra load that the timing gear is put on. So yeah, so anyway, we'll go ahead and install these. We start with the back one first. As far as the other four go, they're all the same. Cam bearings are a press fit. I don't use any Loctite or retainer or anything like that. So there's not enough friction on the cam to really spin anything unless you don't have any fluid going to it, which is its own problem. But we'll go ahead and install this. You want to put firm pressure, make sure that your hole here in the bearing is definitely lined up with that orifice. You want to put firm pressure on your locating cone. That way everything will go in straight. Stop. Give it a check. Got a little bit to go there. Almost there. Okay. That'll do. Pull it out to the next journal. Okay, so the next part, these are your piston oil squirters. You can see the mounting for them down there, and basically, like I said earlier, this ties into your lifter gallery. So those sit in there like that, and there's constant oil pressure to the bottom side of the piston. So helps keep the pistons cool. Any heavy duty engine has them. Just really helps out with heat and keep your pistons intact. I like to take Loctite on the bolts for these and Loctite them in. Some years back there was a group of guys that were on a forum, and when they assembled their engine they forgot to put these in, and needless to say, it's not a very fun thing to forget about these guys in there when you lose all your oil pressure on a freshly built engine at first start there. So go ahead and install these and I'll show you the finished product. Okay, so here you can see the squirter is installed. Now the earlier 6.9 blocks, they actually had press-in squirters, and those aren't available anymore, but you can successfully reuse them. I've done it several times. Basically you pull them out with a pair of grips and slide hammer, and when you install them, when you're putting the engine together like this, you want to make sure that you have some red Loctite on the body of it, and when they seat and you let them sit in, and the Loctite cures, they are almost impossible to get out. So you still can reuse the press-in ones. This is the later style. These were on the later 6.9s and the 7.3s, and even the 7.3 Power Stroke uses the same ones. So that's that. So next thing, what we're going to do is, I think next part here is we'll actually go through and we'll check our bearing clearances for the crank. So stay tuned. Okay, so now we're going to go and check the crank journal diameter. To be honest, I've already checked it. I already know exactly what it is, and I actually have the mic set. But basically, journal diameter on the main journals, spec is 3 inches, 122 thousandths and 8 tenths to 3 inches, 123 thousandths and 6 tenths. That's your range. So you have basically 8 tenths of a range there. And I just got done measuring these. You want to mic them out and then read your vernier. And what I got was 3 inches, 123 thousandths and 2 tenths. So we're basically smack dab right dead center on all the main journals. I haven't checked the raw journals. I want to show you kind of the process. But I'm sure this crank is fine. It's I checked it way back with the other engine, and it hasn't done anything since. So I don't perceive it to have any issues here. But basically, what we're going to be shooting for here on the raw journals is 2 inches 498 thousandths to 2 inches 499 thousandths. So we have an inch, or a thousandth of an inch of tolerance on the rods. So we are, it's like just about 2 tenths. So we're at 248, 2498, or 2498. It's like 24988. So we're looking good there too. So now we'll just go through. I have my mic locked here. We'll go through and check the other side of the journal here. Okay, looks like we're good there. That one's going to be a little tight, which is a little big, which isn't necessarily a bad thing. So we're at the top end of spec there. So that's good. That means your oil clearance is going to be a little bit tight. And on these, because of the nature of the oil pump and that sort of thing, and the way the high volume system works with this is when you're at idle, if you have larger bearing clearances, they tend to run a little bit less oil pressure, which doesn't really mean a whole lot. As soon as you come up off idle, the oil pressure goes right up to where it needs to be anyway. But I tend to like to run, if I can get the mid 20s at idle, at a hot idle on these things, I feel more comfortable with that. And usually it puts you up in the mid 40s, hot running at RPM. So go through and check these. It's a pretty good fit there. Same deal there. And same deal there. So yeah, we're good. This crank's in beautiful shape. So it cranks within spec. Now we'll go ahead and we'll set up the bearings in the block, and I'll show you how we go about doing that. Okay, so I have the main bearings set in the block. I also have the main caps torqued down, and I wanted to show you how I go about checking the main bearing clearance. So basically what you do is, let's see, grab this off here. So you use the mic that you might basically, so you reference off each journal basically, so that you get your dimension like we showed in the previous part of the video, and then you'll actually set your dial bore gauge, which is this tool, and it's a reference tool, but you'll set the length of that measurement end to 0 based on what you got off your crank. And then what you can do is you'll actually come over here to the block and you'll measure that bearing bore, and it'll give you your bearing clearance. Now this isn't going to be an actual measurement. I actually already went through here and measured these, but basically you insert this here and you run that, and this first bearing here, it's coming out right at the top of clearance, so 0.046, 0.0046, excuse me, on the bearing clearance. Actually, we have a little bit less clearance on main number 2. We're back to 0.0046 on the thrust main, and then it's 4.2 for the remaining 2. So right into spec. You actually turn around and you do the same thing for the rods here. And I'm not going to show that just because I gave you the idea. Our crank's on spec. The rods have been resized, so those are all fine. The other way of doing it is you can actually use Plastigauge as well if you don't have these tools. And Plastigauge, you actually sandwich it between the crank and your bearing, and you use the reference on the paper it comes with to basically gauge your clearance. It's not as accurate as doing it this way. You can't judge if your bearings are out of round or anything like that, whereas with that tool you can. But it gives you a rough idea if you don't have these specialty tools on if your clearance is right. So I'm going to go ahead and break this down. We'll get the crank in there and start going from there. Okay, I like to use lithium grease for a lot of the assembly lube. It's not really, it's just kind of a preference of mine. There's lots of assembly lubes that work just fine. I'm not real picky on that. You use motor oil or thicker, more viscous oils. But I like to use Lubriplate. Say it right.
like to put a long bolt. I'm doing this myself, and the crank helps maneuver the crank around a little bit when you go drop it in. Same thing with the caps. Make sure the level's right on the bearings when we're moving it. And in case you're wondering, I slightly oiled the threads, so that's why I'm not putting any on the threads themselves. Make sure on the thrust bearing you get enough lubrication on the thrust surface as well. So there's no front to back location on the mains, except with the thrust in the middle main. So I like to just adjust a little bit, just to keep your fasteners to spin correctly. And it doesn't have to be super perfect, just make sure that your fasteners aren't binding up against the main cap itself.
I like to run my impact on low, 3/8 impact, little Harbor Freight thing. These actually are pretty decent for what they are. I just use this one for assembly, light assembly stuff like this. But I'm pretty impressed for being a Harbor Freight tool. So. Okay. Now we'll go through and retorque them. Start out at 90. So, little side note. The book, specs on the book, it calls for 95. And then you come back and you'll basically take it to 45. I'm not a big fan of the degree method on this. I actually like to take them to 110. They're a 1/2 inch fastener. They don't quite have the length that the head studs or the head bolts have. The factory spec on the head bolts for the engine is 110, and I like to take these, being they're a little bit shorter and a little bit more congruent with the 45-degree angle thing. I like to take them right to 110. I feel more comfortable with them at a torque spec than at an angle spec. And you know, you go one way or the other on that if you want to. And I'm sure if you're an engineer, you can justify it any way you want. But torque is torque, and you know, I like going by a torque spec on them. So go ahead and I actually like to start at 90, and then I'll go to 110 after that. I figure, you know, I like to use 20 foot-pound increments generally when I'm torquing stuff of around this size. It seems to be a good separation, so I'll go ahead and torque them. important part. Make sure that crank spins. And feels pretty good. So, go ahead and flip this over and start installing rods, pistons. Okay guys, so I don't know, I can't remember off the top of my head right now, but I know I've said a bunch of stuff throughout these videos, but I know I went over why I'm using, why I'm basically doing this project anyway. You know, it's in general, it's kind of counterproductive to me to sleeve down a 7.3 block. I think you can sleeve a 7.3 block and maintain 7.3 stuff and utilize turbo rods with big Riz pins and turbo pistons, at least until MALA doesn't want to support this platform anymore, but currently they still do. I guess this will be the future when they decide not to. Or if R&D can make some a universal, I guess, kind of casting of a piston that'll work for both the 6.9 turbo style piston that'll work for both the 6.9 and 7.3, at least the base casting. But that's a little bit in the future at this point in time, until I'm forced to have to do that to keep these things going. So this is kind of the halfway, you know, halfway back sort of thing. The only real drawback to this is the small wrist pins, and again, I don't know of anybody that's had a wrist pin failure directly from too much power. I mean, the rods will always go before the wrist pins go, and based on the size of these wrist pins anyway, I see a piston failure imminent before I see a wrist pin failure. So there's plenty of high-powered vehicles out there with lots more severe cylinder pressures running smaller pins, so I don't see a pin failure being a big issue. That's kind of why we do offer Power Stroke rods pushed down to NA pin size for guys that 6.9 guys and 7.3 non-turbo guys that want to run a beefier rod, that don't necessarily want to step up to turbo size stuff. But these here are turbo rods that we bush down to NA pin size to fit on the 6.9 stuff, and this whole rotating assembly's been balanced. So this was, I think I said 3 years in an earlier video. I actually did the math today. You know, I counted to 3 and 4, you know, for a change. And anyway, so yeah, it was actually 4.5 years ago. It was basically the Thanksgiving, you know, summer to Thanksgiving of 2013 that I did this engine, and the rotating assembly with the other engine. So it's been about 4.5 years, and I've just this rotating assembly's just been floating around. The pistons have a tri-coat on them, which was back before we started doing the piston crowns in house as far as coating and all that. This was done by a place a couple towns over, but they did a tri-coat on this where it's a ceramic top coat. It's got a anti-friction skirt coating, and then an oil shedding undercoating to it. And my opinion on the latter two, the skirt coating and the undercoating, is just not necessary. You can kind of see here some of these. You can see the scuffing. That's with 3,000 miles on the piston with the skirt coating. So I don't see that being worthy of adding to the pistons. They do see a hard side load to them, and obviously the coating can't keep up. As far as the undercoating, when you have a piston squirter constantly spraying oil at the bottom side of the piston, a coating that sheds oil is kind of counterproductive. So I like to stick with the top coating on them. The top coating they use is a little bit different, so it's different color than what we use at R&D, but these are still these pistons are still in really good shape, and the rings are still in good shape. Like I said, it only had 3,000 miles or so on it before I pulled it down because of the head gasket failure with the smaller studs on the other stuff. So basically, I've already assembled the pistons with the bearings and the rings and all that stuff, and they're ready to go in. I want to show you real quick on video here the difference between the turbo rod and the NA rod. I know there's those pictures that float around the internet, but realistically, this is the difference between the turbo rod and the NA rod. You can see the differences in the beam. Obviously the wrist pin, And like I said, that's not that much of a concern. But the lower part's pretty similar. 1 second here. Okay. So I didn't have a complete Power Stroke rod. This one is just the mismatch that we had laying around. I thought I had a couple of sets of cores here, but I couldn't find them in the boxes and all that right at the minute. So for video's sake, I just grabbed this one. Obviously you can't tell, but the Power Stroke rod has 7/16 fasteners down at the bottom instead of 3/8 like the IDI. So it's a little beefier in that sense. But if you look at the actual beam itself, you know, the rest of it, factory turbo rod is basically as stout as a Power Stroke forged rod. So these right here are good to 400 at the wheels. These right here on a Power Stroke, which is a DI and sees a little bit higher cylinder pressures, is good to, you know, anywhere from 600. There's guys who push them way higher than that, but the general rule of thumb is about 600 for those. And so I don't see any reason that a factory turbo rod itself wouldn't be good to 550 or 600. I have, well, I mean, this particular engine's never going to see anything close to that. You know, 400 wheel horse at the tops, I would say. And it's just because I'm building it for longevity, and that's, you know, that's how this engine's going to go. My Bronco, for you guys who are familiar with that, is running Power Stroke forged rods, and we'll see where those, how far those things last on an ID engine soon enough here. So, but that gives you an idea of the difference between the rods there, you know, on video, 3D instead of in a picture. So, yeah. So what we'll do is clear the bench off here. I will start pulling caps off these things. One of the other things I wanted to go over is some guys will dip their pistons in oil and all that stuff, and I don't feel that that's necessary. I like the rings to start seating immediately, and that means you need a semi, you know, thinner fluid, and you can debate that all you want once again, but basically I like to use like brake fluid or ATF to coat the cylinder walls during installation here, and that kind of helps the rings kind of start digging in real early. Not that it really matters a whole bunch once you really get it going. The piston squirrels start coating the walls, you know, through the oil rings and all that, and you'll get the normal lubrication. But to really get the rings start to bite in, I like to use a thin oil. Some of the guys in the motorcycle world don't even use anything, so if that says anything. But WD-40, brake fluid, ATF, I like to use that sort of stuff to coat the cylinder walls during installation. So I'll go ahead and start getting to that, and set the camera to the side and let you guys watch. Okay. For those of you guys who've never built an engine before, I don't know if you can see it or not. It's hard to judge the angle here. There's a chamfer on this side. That goes to the radius side of the crank. Okay. The other side is the adjacent rod. So this goes to the radius side of the crank. So all of them go the same way. So in terms of the IDI, if you look at your pre-chamber ditch, your like for lack of a better term, it's the ditch, your Ricardo cut here. If that goes up, doesn't matter what cylinder it is, that pointing up the way it should go, that means your chamfer is going to be to the right side. Okay. Okay. So the next step is going to be to install the camshaft and degree it in. First of all, crank around so that the dot is vertical. Cam we're running in this is the stage 1 grind. We'll go through and we'll throw the degree wheel on it too, just to verify that we're in where we need to be. Typically we run, you're supposed to install this cam at a 111 to 112 intake center line. That's to get the events where it should be, and what that requires on these particular engines is to actually retard the camo tooth. We'll go in and we'll degree it in to see how close we are just retarding a tooth from there. You can get offset Woodruff keys, but they're kind of iffy. That said, if you're within a couple degrees each way of 112, 111, 112, then it's not going to make that much difference. But you really need to check to make sure it's not like 119 or somewhere around those lines. So, but we're going to try and get it as close as we can to 111 or 112 on the intake center line. And that way the cam events, all the valve events and everything are where they're supposed to be with this particular grind. Okay, so we're at 1 tooth clockwise from the crank. Okay, so that's 1, 2, 3 parted. Already just adjusted. RD, this is Justin. Hey, how's it going? Okay, so we just visually set it to 0, and then I'm going to come back around. We'll check it at 30, and then we'll bring it back around and check it on 30 at the other end. After we get our pointer on, that way we can verify exactly where top dead center's at. Okay. Okay, 7 degrees after top dead center. We'll run it around until we hit 30 on the other side and check where that is and verify that that's 7 degrees before top dead center. So it looks like we're about 3 degrees off. That's 10. So that means that we're going to go back and we'll set it to, basically we're going to move the pointer just clockwise. See, no, counterclockwise. Set it to TDC, move it counterclockwise. Basically a degree and a half here, and then we'll reset to TDC. So. R&D, this is Justin. Okay. Now we'll verify that again. So there we are, 8.5, so there's our degree and a half there. And we're 8.5 there, so that means top dead center is top dead center now. So now what we'll do is we'll set up a lifter in here. I'm just going to measure, I'm going to rotate it around until that lifter comes up to its highest point, and that'll give us our intake center line. Okay, right there. So we are top dead center, 90 degrees, 100 degrees. Intake center line is right at 109 on this one, so that's close enough. It's almost 110, it's like 109 and a half. So we are good to go as far as that goes. Now, like I said, it can range a little bit one way or the other, and it's not going to affect the overall characteristics of the cam that much, but it's always good to do this and degree the cam, and just so you know exactly where you're at. So next, go ahead and install the lifters, the spider, and all that stuff. I'm going to get this stuff off here, and then I'll start filming that, and then we'll go ahead and we'll set the heads up. Okay, lap the valves in now. A lot of times this isn't even necessary. Valve job itself with the machine is good enough, but I like to verify it. Make sure that everything's seated in properly. Good. All those felt pretty good. That looks good. We need to do that last one a little bit more. Some high spots. It looks like it may have a little chatter there. So be all right. Okay. Okay, this is a spring height tool. That way we can judge how far we need to shim the valve springs. So that one, we are right at 181, so we're about 10 thousandths, 15, so yeah, 15, 14, so 1.814 is where we're at there. So I'll throw a 15 thousandths shim in there on that one. So, maybe so those are the 15s. So rotator out, shim goes under the rotator. And that one's ready. Go into this, shooting for 1.800 across the board on all of these. So usually the exhausts are a little loose compared to the intakes. The intakes are normally a little shallower on the stock ones. These intakes, because we modified them like in the previous video, are going to sit a little lower. So basically they won't have you won't have as much pressure there. So go ahead and check this intake. They're just COM 910 springs. It's kind of run-of-the-mill stuff we use. One down, one to go. So I'll probably do the other head off camera, but you guys get the idea here. So. All right, so we're gonna torque the head down now. Heads down. ARP studs, top torque rating on them is 125 foot-pounds. I like to go, and any of you who have my stud kits know that I like to go a little bit more than that. 150 is a good level for these. I've tested them up to a 180 before you hit yield on them. ARP has kind of a CYA factor built into their studs and fasteners in general. So take them, get a little bit more clamping load out of them by over torquing them, and never had a head gasket failure yet with studs at that level. So I'll go ahead and go through. I'll go through this side. No reason to show both sides, but I like to start them out at 85 as the first step. 80. Okay. And these heads are pretty simple. Start at your middle bolt here, and you basically just spiral out. That's how IDI heads are torqued down. So. And finally, jump up to 150 for the final pass. And this is the fun one. Whew. Now I like to go back on a line pattern. Just verify they're all at 150. There you have it. plenty sufficient to hold those heads down under almost any circumstance. So so I like to run into there. Go ahead and do the other side, and what we'll probably end up doing is kind of buttoning things up. I don't think you guys really need to see water pump installation and all the miscellaneous little stuff. So what I'll probably do is I'll just cut in with the finished product before it goes into the truck, and then the next part will be a road test after it's in and everything. So anyway. Okay, so here's the engine all together. Ready to go in. I will have a list of the final build on this thing. And then next video we'll take it for some drive time. So anyway, enjoy.